Hey everyone, Dakota here from basementbiotech.org. I'm going to be doing a video on a circuit my friend Jake and I have been working on for the past couple of months. This circuit is based partially on Russell Durrett's light bulb PCR machine, whose link you can find in the info below. Before I start, I just wanted to thank Avery Louis from the DIY Bio forum for helping me choose the relays, which is this blue box here. Everyone else in the DIY Bio forum has always been very helpful over the past couple of years on numerous projects, but there's too many people to name. Another person whose project you can check out is Cathal Garvey, who made a similar thermocycler which used a heat gun instead of a light bulb as the heat source. So this whole circuit is basically based around using a microcontroller as the brains to switch a relay here which controls the current to a high voltage, high current device like a light bulb. Now the Arduino itself can only put out 5 volts and I don't even think an amp of current, so it's not enough to power an actual light bulb. So what we use is a relay instead with a transistor circuit. So this whole circuit is basically made up of 2 different circuits. We have an analog circuit which is based on the thermistor, the voltage divider with a 10k ohm resistor, and then the digital circuit whose output is based on the input of the analog circuit, measured in degrees Celsius basically in this case. So when a particular threshold temperature is reached, the analog circuit puts an input into the microcontroller, which then puts an output into this yellow wire here, which is at the base of an NPN transistor. Now the transistor allows for more current to flow from the 5-volt rail of the Arduino through the coil of this relay here. Now relays are mechanical switches that can allow high current, high voltage devices to be turned on and off, which with low current, low voltage devices. So this relay can be switched on with 5 volts and maybe 40 to 50 milliamps. And it controls up to 5 amps of current and 250 volts. So in the future, this blue box here will be soldered into a circuit which goes inside of a protective box like this, wired in series with an adapter like this, which will allow the 120 watt light bulb to sit in there. So in order to protect the microcontroller from voltage kickbacks of the coil collapsing, we have a reverse bias diode placed across the relay here. Now if you want to look at the temperature of this light bulb, which is only 14 watts actually, it's sitting just below 70 degrees centigrade, and that's only 14 watts. So our light bulb is going to be 120 watts. It should be able to put out a little bit more heat than that. Now this green LED is always on because it's representative of a light bulb or high voltage, high current device that will be on in the future. So in the code I've set it up just for this demonstration such that the current is always flowing through the circuit when the temperature is below 24.0 degrees, and it's always off when the temperature is above 24.2 degrees. You can see now the temperature is just about 22.5 degrees Celsius. So right now I'm going to put my hands on the thermistor to heat it up, and you're going to be watching for the LED to turn off and the relay to switch just like that. So now I'm going to let go of the thermistor and wait for the thermistor to cool back down. So when that cools back down, it's at 25.7 degrees right now. When it cools back down to below 24 degrees, you'll see the circuit turn back on. So remember, think of the LED as the 120 watt light bulb, which is heating up our reaction mixture. Once it gets to a specific cutoff temperature, in our case for a thermocycler it might be around 90 to 93 degrees centigrade, it's going to turn back off. Now you want to have a difference in temperature inside the code such that it's not bouncing back and forth on a particular temperature cutoff. That's why you always want to put in a hysteresis loop. So vary the code cutoff from between 1/2 degree to 1 degree based on your application. So right now we're at 24.73 degrees centigrade. Once it drops back below 24 degrees, we should see the circuit turn back on. So again, another overview while we wait for that. The thermistor is measuring the temperature of the environment. That input is going across a voltage divider here with a 10k ohm resistor. That's being read through this blue wire by the analog input of the microcontroller. Once the microcontroller sees that a certain temperature cutoff has been reached, right now 24 degrees, the circuit turns back on. So when it sees that a certain temperature has been reached and the relay turns off, that sends an output through this yellow wire here into the base of the transistor. Transistors are basically switching devices which can transport more current, basically. So the higher current comes through the 5-volt rail, through the transistor, through the coil of the relay, and into the LED. In the future, the LED will be replaced by our high voltage, high power device, namely the light bulb. And by controlling the code, we can turn the light bulb on and off, as well as another device, probably a 12-volt CPU fan cooler, turn that on and off, and allow us to heat and cool rapidly within a few minutes per each cycle our PCR samples. So that's basically an overview of the circuit as it stands right now. Sorry for the camera shaking around, and if you continue to watch, you'll see an update on some new videos when everything's built, and I'm probably also going to make a video splitting this circuit apart into the digital part, which is the relay, the transistors, and a few resistors, and also the analog part, setting up a thermistor to just measure temperature. So thank you for watching, and thank you for all the help if you've ever contributed anything on the DIY Bio forum or anywhere else.